Europe's Galileo constellation forms the world's most accurate satellite navigation system, delivering metre-scale accuracy to more than 3.5 billion users all across planet Earth. At the core of the Galileo system is a constellation of satellites in orbit, sufficient in number that enough are visible in the local sky to perform accurate positioning anywhere on Earth. The satellites are each about the size and shape of an old-fashioned phone booth, with main antennas that stay locked onto Earth, continuously transmitting navigation signals.
We have 4 clocks on board the satellites. 2 of them are the passive hydrogen maser, that is the most accurate clock that has ever been flying to space, and it has an accuracy, think about it, of 1 second every error every 3 million years. So very accurate, and it's thanks to that Galileo is one of the most accurate global navigation satellite systems.
But it all starts on the ground, and more precisely at ESA's ESTEC Test Centre in Noordwijk, the Netherlands. It's the largest satellite test establishment in Europe and hosts a collection of equipment to simulate all aspects of the space environment. It is here that the vast majority of Galileo satellites have undergone testing to prove their readiness for flying in space.
During space simulation, the satellite is installed in a space simulation chamber where we are trying to reproduce the same conditions in space. This means vacuum and extreme temperature. Temperature can go down as cold as minus 200 degrees that we are reaching thanks to liquid nitrogen which are pumping through the chamber. We need 40,000 liters of liquid nitrogen to be able to reproduce the space conditions for Galileo per day. To reach the extreme hot conditions, which can be well above plus 50 degrees C, we are using gaseous nitrogen that we are warming up thanks to electrical heaters and circulating in the same shrouds. The satellite would stay typically 2 weeks in these conditions to be able to cover all the operational mode of the satellite.
One of the most important tests is electromagnetic compatibility. All satellite elements are turned on within the radio-shielded environment of the Maxwell test chamber. Its foam-covered walls absorb radio signals, preventing any signal reflection, to mimic the infinite void of space. The aim is to ensure that all parts of the satellite work well together, with no harmful interference. A successful test campaign means each new satellite is classed ready to join its counterparts in orbit, extending the reliability and performance of the world's best performing satellite navigation system.
The next step would be that the solar arrays are mounted in a folded position, and the satellite would be submitted to the mechanical environment it would experience during launch. It is put in an acoustic chamber where incredibly big loudspeakers reproduce the acoustic noise that is made during a launch, and these sound waves have a big impact on the structure, and we want to verify, for example on the solar arrays, that they can withstand without any problems this high level of sound waves.
Here, the solar wing of a Galileo satellite is deployed. The 1 by 5 meters long solar wing supplies about 1.9 kilowatts of power, about the same as an average European household's consumption. Mounted onto these panels are more than 2,500 state-of-the-art gallium arsenide solar cells. A counterweighted rig supports the deployment. Otherwise, the delicate fold-out wings, designed for the weightlessness of space, would crumple under the pull of Earth gravity.
What we see here behind me is a satellite with its solar array deployed, and it is reaching the end of the testing campaign. So it's gone through all the phases of thermal vacuum, acoustic, and we verify here that nothing was damaged. So we show that the solar array after the acoustic and mechanical tests can properly deploy, and we check that the performance is still good. So we shine a bright light on it to see that all the cells are still intact and that there was no damage.
We have developed the system from the very beginning, measured the performance with the first elements, so we were actually very aware that the Galileo would deliver excellent performance because of the technology which is contained within the system. We have already started the first steps for deploying the next generation, second generation of Galileo, which will consist of more powerful satellites, satellites which will deliver additional services. They will also be reconfigurable in orbit, so this gives us a lot of flexibility, and we can adapt the services of the system to the market needs. And that really is an innovation that we will bring into Galileo.
Besides the satellites, of course, the ground segment plays a very important role. It is a worldwide distributed ground segment with stations all over the world. This is why Galileo is a global navigation satellite system, and in particular, two control centers. One in Oberpfaffenhofen in Germany that is devoted to the command and control of a spacecraft in the constellation as primary function, and another one in Fucino in Italy that is devoted to navigation control and navigation message generation and dissemination to the satellites.
Galileo, the European Satellite Navigation System, is the fruit of a partnership between the European Union, who owns and funds the programme, ESA, who develops and designs the entire system, and EUSPA, who oversees exploitation of services to end users.